Now that we've got an idea of what a function of multiple variables looks like, let's talk about limits. So first off, I will ask you to recall with me the idea behind a limit. So for functions of one variable, we had this idea. The limit as x approaches a of f of x is equal to some value L. It means that for a given function, even if it doesn't necessarily actually hit that value, as x gets really, really close to a, y gets really, really close to the value of L. Doesn't necessarily have to be an open circle, doesn't necessarily have to be a closed circle, doesn't actually matter. So the idea behind a limit is we can make the value of f of x arbitrarily close to L by taking x to be sufficiently close to a. We can make the value of the function as close to L as we could possibly want by taking x sufficiently close to a. So we can get as close to L as we want by simply getting close to a. Close, of course, being a relative term. Now, additionally, when we allowed x to approach a, there were really only two ways to do this. X could approach a from the left-hand side, and x could approach a from the right-hand side. Those two together would be a two-sided limit. Individually, we refer to them as one-sided limits. So now, if we were to bump this up to the next level, we could say take the limit as the ordered pair xy approaches a, b of a function of two variables is equal to L. Now, we can interpret this to mean we can make the value of f of x arbitrarily close to L by taking the ordered pair xy sufficiently close, man, spelling is hard, close to the ordered pair AB. Now here's the issue that we run into. If I wanted to consider the ordered pair AB within the xy plane, we'll call this AB, there are lots and lots of different ways to approach this point when you have access to two dimensions. When you only have access to one dimension, as x approaches a, you can only approach from x is less than a or from x is greater than a. Down here, there are all sorts of different ways that you could approach this point. You could approach from above, from below, from the right, from the left, on a diagonal, on a parabola, on a cubic. There are lots of different ways to approach a given point. So how do we know how we are approaching a given point? And for that, we are going to give the following definition. A path is a planar curve passing through a given point. A path is a planar curve passing through a given point. Now, through does not mean terminating at a point. It means you have to actually pass through the point. So for an example of paths, if I wanted to consider paths through the ordered pair 2, 4, for example, there are a couple pretty straightforward ones, like we could pass through on a vertical line. We could pass through on a horizontal line. Those are certainly possible. We could do a straight line that passes through the origin. Y is equal to, say, 2x. We could do y is equal to x plus 2. We could do y equals x squared. We could do y is equal to the square root of 8x. There are lots and lots and lots of different paths that will all pass through the given point. Now, given that there are so many different paths, does that mean that we would need to approach on every single path? The answer is no, because there are an infinite number of paths that will pass through any point within the Cartesian plane. So instead, we have the following theorem. If on two different paths the value of a limit approaches two different values, then that limit does not exist. And an abbreviation that I would hope you're all familiar with, DNE, standing for does not exist. So if you can find two different paths along which a limit approaches two different values, then you have proved that the limit does not exist. It's sort of like back when you had access to a function, if it was a different function value from the left as from the right, that was also a case where it does not exist. The difference is we're just looking for two different paths. You only had two paths from the left and from the right when we were dealing with limits back in Calc 1. Now, what this does not mean is that if you test, 10 different paths and you get the exact same value on every single path, that the limit does exist. Paths cannot show that a limit does exist. Paths can only be used to show that a limit does not exist. I will demonstrate that with a couple of example problems.